we will be talking of some algorithms for what is termed as polygon filling. Last time we had seen some algorithms for drawing lines between 2 points. If you want to draw a line between 2 points, we can use either the DDA algorithm or the Bresenham's algorithm. Now, if you have to fill a polygon, let us say if you have a polygon like this, filling the polygon means all the pixels that are inside the polygon, they should be highlighted, okay, and all the pixels outside, they should remain off. So, it is essentially some form of either shading or you are familiar with hatching in drawings. So, if you want to hatch a given area, a closed area, that is done by using filling algorithms. So, filling essentially means that if I cover this polygon row by row, okay, if I take the first row of pixels, these pixels which are inside, they will be on, then these pixels will be on, these pixels will be on, and so on. Okay, so we have to decide which pixel is inside and which pixel is outside. What we are given for this is a polygon, and what is a polygon? A polygon will be defined as a list of points. Okay, so if you have a polygon like this, this would be represented as a list of points given like this. Okay, so if you have a list of points, then a polygon filling algorithm will highlight all the points which are inside the polygon. The polygon need not be a simple convex polygon like this. It can also be a concave polygon like this. So, in the case of a concave polygon, similar thing would be done. Okay. For the time being, we will see algorithms which are going to fill the area by a set of highlighted pixels. We are not going to see algorithms which are going to hatch a given area. If you have a, let us say, area like this and you want to do hatching, we will have to draw lines, let us say at an angle of 45 or at some angle or some other hatch pattern inside this closed area. Okay, the same polygon filling algorithms can be modified for this purpose also. We won't go into that for the time being. Initially, we will see algorithms for filling an area, which means highlighting all the pixels and getting a complete filled or a shaded view of this polygon. Okay. The type of algorithms that we will see in this are what are called as scan conversion algorithms. In these algorithms, if we have a screen like this, we will start from the top row. Within the top row, all the pixels that are there inside the polygon, they will be displayed. From that top row, we will go on to the next row and so on. Okay, so we will go through all the pixels, but row by row. Okay, a row of pixels, let us say this is a row of pixels, is normally referred to as a scan line. Okay. So, our job would now be that if we are talking of a particular scan line, let us say we are talking of this scan line. In this scan line, we have to find out which pixels or which sequence of pixels are going to be displayed. In this case, we consider this point 1 and point 2. All pixels from point 1 to point 2 will be displayed. If you are talking of a scan line over here, all pixels between 1 and 2 and between 3 and 4 would be displayed. Okay, so this portion Okay, so often we can have on a single scan line we can have more than one set of pixels being displayed because we are talking of concave polygons. Okay. Now, if we notice as we move from one scan line to a second scan line, let us say initially we are at this scan line. Okay, this is my scan line number I and this is my scan line number I plus 1. What can happen as I go from one scan line to a second scan line? In scan line number I, no pixels are inside the polygon, but on scan line I plus 1 we have a vertex which is there on this scan line. Okay. If I am on this scan line, let us say which is scan line number j, and I go on to a new scan line which is scan line number j plus 1. This point 1 is being modified to 1 prime and this 2 is being modified to 2 prime. Okay. Initially from 1 to 2 all the pixels were on, now from 1 prime to 2 prime all the pixels will be on. What is the difference between lines j and j plus 1? The point 1 has been modified by an amount equal to the slope of this line. Okay. The difference between 1 and 1 prime is this amount, and similarly the difference between 2 and 2 prime is this amount. Okay. So, in a case like this, when we move from one scan line to the next scan line, the position of the edge shifts by an amount equal to dy by dx or delta y by delta x. Okay. So, as we move from one scan line to from one scan line to a second scan line, one of the two things happen. First is for all intersection points, the intersection point would shift by an amount delta y by delta x. Okay. Or the other thing that can happen is as we move from one scan line to a second scan line, new edges can start. Okay. Or an edge can come to an end. Okay. So, we will say as we move from one scan line to another, the intersection points will change by an amount of delta y by delta x, and the edges would start or end. There are two kinds of things which can happen. For instance, here two edges will start at this point, one edge is coming to an end and a second edge is starting. Okay. Similarly, here two edges would start. At this point, two edges will come to an end. Okay. As we go from scan lines in these positions from here to here, the intersection points will change by an amount equal to delta y by delta x. So, if you are able to keep track of these changes, in that case, from one scan line to second scan line, we can keep deciding what are the pixels which are inside and what are outside. Okay, if you know which are the pixels which are inside at this scan line, at the next scan line I will only change the intersection points by amounts equal to the slope of the edges. Okay, if I know that at this point two edges are going to start, I will just take care of these two edges and I will compute their intersection points and display all the points which are inside that. Okay. At any point, if I know that the set of intersection points on that scan line are, let us say, 1, 2, 3, 4. If I know the set of intersection points, okay, the intersection points if the intersection points are, let us say, let us call them Q now, or I1, I2, so on till In, that is 1, 2, 3 and 4. These are the 4 intersection points on a given scan line. Then which are the pixels which are going to be displayed? Pixels lying between I1 and I2, they have to be put on. Okay, between 1 and 2 they will always be on. Between 2 and 3 they will always be off. Okay, alternate pairs of pixels or alternate sets of pixels will be on and off. Okay, so this is the first set of pixels, this will be on, the second set of pixels, this will be off, the next set will be on, and so on. If we have a polygon which is like this, we are considering a scan line at this point 1, 2, 3, 4, 6, 7 and 8. Between 1 and 2 they will be on, 2 and 3 will be off, 3 and 4 will be on, 4 and 5 will be off, 5 and 6 will be on, 7 and 8 will be on. Okay, so alternate pairs of or alternate sets of points will be on and off. Okay, so what we will do is at every scan line we will try to keep track of these intersection points. Okay, how do we do that? Let us see the algorithm. Algorithm for scan conversion of polygons. What is given to us? A polygon has a list of points. Again, what do we have to do? What is the aim? To fill the polygon. Okay. Okay. The way we will do it, let me first explain the data structures involved. We know this set of vertices. Okay, we know that at every vertex there will be two edges which will be coming. Out of these two edges, we can have number of cases. Either both the edges are just going to start at that scan line. Okay, like in this case, this edge is also starting, this edge is also starting at this scan line. At this scan line I plus 1, let us say this edge as well as this edge, both the edges are starting. If I consider this scan line, one edge is starting, one edge is ending, the other edge is starting. At this point, both the edges are coming to an end. Okay, so at each vertex will always have two edges, and they can either be starting or ending. Okay, so what we will do is we will keep track of the vertices or the scan lines on which the vertices are occurring. Okay. If I know that on scan line number, let us say 10, a particular vertex is starting, then moment I come from scan line 9 to 10, I will take up all the edges which are on scan line number 10, which are starting at scan line number 10, and I will start taking care of them. Okay, so as I come from, let us say 9 to 10, and I know that at 10 two edges are going to start. Okay, so that will help me in taking care of the intersection of these two edges. Similarly, let us say from as I go from scan line 50 to 51, I know that two edges are going to end in that region. So when I go from 50 to 51, I will delete the intersection of those edges and not bother about them anymore. Okay, so at every scan line we will keep track of the vertices that are there on that scan line, and we will also keep track of the set of intersections on that scan line. Okay, so that will be done in two different structures. The first step in this algorithm would be that we will sort the vertices as per the y coordinate, and okay, what this means is, I will just put that back. We have a set of scan lines number 0, 1, 2 and 3 and so on. Okay, we want to know whether there is any vertex starting on scan line 0, any vertex on scan line 1 and so on. Okay, so we will maintain an array which is conceptually something similar to a bucket. In that array or in that data structure, whenever there is a vertex on a particular scan line, like this vertex is on scan line number 2, so this vertex will be kept in the bucket number 2. In some sense it is going to be a queue of events. So let us say we have an array called bucket of I, and bucket of I is going to contain a list of vertices at scan line number I, at row number I. Okay, so let us say if we have a case like this, okay, this is P1, this is P2 and this is P3. So what we want is bucket of 0 should be empty, bucket of 1 should also be empty, bucket of 2 would contain one vertex which is P1, okay, bucket of 3 would contain two vertices P2 and P3. Okay, and so on. So, if the y coordinate of a particular point is I, that point, or we will keep track of that point in bucket of I. Okay. So, if we have a, let us say n pixels, sorry, n vertices, each vertex will be stored in some bucket. Okay. So, n locations in these buckets are going to get occupied. Is that clear? The basic idea is that at scanline number I should know what are the set of vertices starting on that particular scanline.
Isn't this sort of memory inefficient? Like,
Again, please.
isn't this memory inefficient? If we have so many buckets in which most of them are empty.
Isn't it memory inefficient? It is time wise very efficient. Okay, because you are able to find out on which particular scanline which points are there. Okay, and for doing this kind of sorting, you are able to do it in time which is proportional to the number of points. Okay, this process is referred to as what is called bucket sorting. Okay, the amount of memory used will be equal to the number of scan lines. Okay, that will be the array size. The speed will be proportional to the number of points. Otherwise, if you do sorting in any other way, the speed will be much slower than that. The time required will be more. Okay. So, in each bucket we will have the set of points starting on that particular scan line. So, that is what it says, sort vertices as per y coordinate and place them in the bucket for that coordinate. Okay. So, bucket of I would have list of vertices starting at, or list of vertices with y coordinate equal to I. Okay. Then I mentioned earlier that we need to keep track of two things. One is on a particular scan line, which are the vertices which are there. And the second thing that we need to keep track of is on a particular scan line, what are the sets of intersections. Okay, intersections, or what are the sets of edges which are active. If a particular edge is active, that means that edge is intersecting the scan line. So, the first part of the algorithm is taking care of telling us on a particular scan line which are the vertices which are occurring. Okay. The second part of the algorithm now, that will tell us the intersections on every scan line. What we will do is, if we have a set of intersections, we will maintain what is called an active edge list. Okay, or we will refer to it by AEL. So, this AEL, active edge list, will store the list of active edges. And the intersections on a particular scan line. Okay, so in this case our intersections are 1, 2, 3, 4. This active edge list is going to maintain that these 4 edges are intersecting and the intersections are so and so. And as we go from one scan line to a second scan line, we will keep updating this active edge list every time. Okay, so the steps in the algorithm would be like this. We have already placed the vertices in the buckets. Now, step 2 is for each scan line, SL I am keeping for scan line, for each scan line I, the first thing we will do is examine bucket of I. Okay, we will first check whether there are any edges which are starting in that particular scan line, or if any edges are coming to an end at that scan line. Okay, so if there are any edges which are starting at that scan line, what will we do? If edges are starting, then we will add the edges to active edge list. Okay. If there is any edge which is starting on that particular scan line, that will be added onto the active edge list. Okay. Then for each edge which is already in the active edge list, what should we be doing? These are edges like this edge and this edge. Okay, at this particular scan line, this edge is already in the active edge list and the intersection point for this is 1. Okay, this edge is already in the active edge list and the intersection point is 2. As we go on to the next scan line, we should change the intersection points. Okay, we should modify the point of intersection by an amount equal to delta y by delta x. Okay. So, for each edge already in the active edge list, update intersection point. Okay. Incidentally, when I mentioned here that this amount is equal to delta y by delta x, it will actually be delta x by delta y. Okay, because we are moving in the y direction. Okay, and the movement in the y direction is equal to 1 pixel. So, the movement in the x direction is going to be delta x. Okay, or delta x by delta y. Okay, but the basic idea is that the movement will be proportional to the slope of the line. Okay. So, we said for each edge already in the active edge list, update the intersection points. Okay. Now, while we are doing this, we should take care that all intersections are maintained in an increasing x coordinate or remain sorted as per x. Okay. If we have intersection points 1, 2, 3, 4, we should always maintain them in the increasing x order. Okay, because we have seen that alternate sets of pixels are going to be on and alternate sets would be off. Okay, so we should take care that these intersections are maintained in an increasing order of x. Okay, so whenever we add a edge to it, we'll add it such that it remains in the increasing order of x. Okay, so at this point, at this scan line, we had an intersection here 1, intersection here 2. Now 2 edges are being added here at this point. So let us say these edges are A and B. So we won't, the set of intersections should not be 1, 2, A and B, it should be 1, A, B and 2. Okay, they should remain sorted as per x coordinate. Okay, so for each edge already in the active edge list, update the intersection points, and while maintaining the intersection points, we have to be careful about keeping them in the increasing order of x, keeping them sorted as per x. Okay. Then the third step of the algorithm, or sorry, not the third step. For each scan line, we've done this. So 2, 3. The third part of the second step itself. At this stage, we know the set of intersections on a particular scan line. Okay, the set of intersections is known. So now we'll say display alternate regions of alternate regions or alternate sets of pixels. Okay, so in the active edge list, if we have intersection points given by x1, x2, x3, so on, and between x1 and x2 we should display, x3 and x4 we should display, and x5 and x6 we should display, and so on. Okay, and this process will keep repeating for every scan line. Okay, for every scan line we'll keep repeating this till we reach the end of the screen. Okay, so this way we will be able to fill the polygon such that all the pixels inside would be highlighted and all outside would not be. Is that okay? Any question on this up to what I have covered so far? Then we will see some more details of this algorithm.
So how do you find out, you in step 2.1 you said for an edge starting.
Yeah, in step 2.1
You said if edges are starting.
If edges are starting, what happens when edges are ending?
How do you test for this, edges are starting or ending?
How do you test whether edges are starting or ending? That is quite straightforward. See, this is a particular scan line. You have a edge given by pi plus 1. Okay, the y coordinate of this is, let's say, yi, this is yi plus 1. If yi plus 1 is greater than yi, the edge is starting. If yi plus 1 is less than yi, the edge is coming to an end. Is that okay? Because we are moving in this direction. If our line is like this, okay, this is pi and this is pi plus 1 or I minus 1. Okay, this, in this case, yi plus 1 is less than yi, so the edge is coming to an end. Okay, here yi plus 1 is greater than yi, so the edge is starting. This is the case of the edge starting, this is the case of ending. Is that okay? Any other point? Okay. Now, in this algorithm, if you noticed, we are maintaining this active edge list, and in the active edge list we are computing the intersection point of every edge. And as we move from one scan line to the next scan line, this intersection point is being modified. So, this active edge list is going to contain a list of edges, okay, a list of entries. So, we will have something like this, and so on. Okay, this is going to contain all the information for the first edge, edge 1. This contains all the information for edge 2. This contains all the information for edge 3. Okay, we said for each edge we need to know what is the intersection or the x intersection at that particular scan line. We also need to know what is the slope of the edge. Okay, so this entry in the active edge list needs to contain some information. The first information would be the x intersection. Okay, so this is let us say scan line numbers, and on this particular scan line, let us take it something like this. We have entries for this is edge E1, this is edge E2, and so on. For this edge E1, we need to know the x intersection of edge E1 with this scan line. Okay. We also need to know that as we move from this scan line to the next one, by how much is this intersection changing. Okay. As I said, at this particular on this scan line, on this line, this is the intersection. On the next scan line, this would be the intersection, and the amount that is this difference will be how much? It will be some delta x. Okay, so for each edge in the active edge list, we will also have to store the delta x. Delta x is the amount by which the intersection would change as you move from one scan line to a second scan line. Is that okay? So, we need to know x and we need to know delta x. Do we need to know anything else?
The endpoints.
You need to know when the edge is coming to an end. Okay. How do you keep track of that?
You have the list of points P1, P2, P3.
You have the list of points.
P1, P2, P3.
Okay. Any other way? Any other way in which you can keep track of the endpoint of this line?
So if delta x is 0 for some particular point,
Delta x is 0.
Then-
Delta x depends on the slope of the edge.
I mean, it shows that there is no other point ahead of it.
There is no other point.
Yeah, like the line is ending, and if there is no point, delta x will be 0 for that.
So we store yi
You store
plus 1 or something,
yi.
whatever, wherever it's ending.
Okay. You store the endpoint, right? So this is the starting point. You also store the endpoint, and every time you will keep comparing whether the endpoint has come or not. Instead of that, what you do is you store the number of scan lines remaining. Okay, so at this point the scan line has started. You can compute the difference between the y values between the starting and the end point, and keep that y value over here. So this y value is the number of scan lines. This the number of scan lines remaining. Okay, number of scan lines remaining. That means this is the line, it has started at this particular scan line, which is scan line number I. Let us say this is point pk, this is point pk plus 1. The y coordinate of this point is I, and the y coordinate of this point is, let us say, j. Okay. So, the moment this edge starts at this point, the number of scan lines remaining would be these many, which is j minus I. Okay. So, this would be the value of y, that is the number of scan lines remaining for this edge. Yeah.
Any other reason for us to maintain the number of scan lines remaining? Why don't we just store the end point, the y of the end?
Let me just complete that, then I will answer your question. Okay. So, this is the number of scan lines remaining. As we go from one scan line to the next, we will keep decreasing this number by 1. Okay. So, number of scan lines remaining would become less by become 1 less every time. Okay. The moment this number becomes equal to 0 or becomes less than 0, you will delete that edge. Okay. So, with every edge we will also keep track of the number of scan lines remaining, and every time we go from one scan line to a second scan line, we will be decreasing the value of y by 1, and if this happens to become negative at any point, that edge has to be deleted. Okay. So, the corresponding modifications you can make in the algorithm, that is, we have said update intersection points. Along with that, we will also have to update y. Okay, we will have to say y will be equal to y minus 1. For each edge in the active edge list, we will have to say y equal to y minus 1. And in the beginning, when we are examining the bucket for new edges, in addition to this, we will also have to examine whether some edge has come to an end. Okay. Or we can examine it right here before updating. We can examine whether y coordinate is less than 0. If it is less than 0, you can simply delete it. Okay. At this point, we can do that. Okay. So, we are adding edges in the active edge list according to the bucket. We will be deleting the edges if the value of y becomes less than 0. Okay. And as we go from one scan line to a second scan line, we will update the intersection points and we will delete edges which have come to an end. Okay. We will make sure that all intersections are maintained in the increasing order of x. Okay. And after that, we will display alternate sets of pixels. Okay. Alternate sets would be on, alternate sets would be off. Okay. Now, coming back to the questions you had asked. Any reason for maintaining y and not just the endpoint j? See, if you are maintaining the endpoint j, at every scan line you have to compare the y value with j. Okay, but now you will be subtracting 1 every time, and the moment the number becomes negative, you can delete that. Okay, checking that is computationally easier.
Subtracting 1 is easier to comparing.
Comparisons are quite expensive. An if statement is much more expensive than a subtraction
and comparison.
No, comparison with 0. So, you are only checking for the sign bit.
No, but the overhead is we have to maintain a subtraction also, decrement.
Decrement by unit amount.
So
Decrement by unit amount plus comparing the sign bit would be cheaper. Okay, it's basically for efficiency considerations. conceptually you can always compare it with j every time. Okay, but comparing two abstract numbers, I mean arbitrary numbers, is more expensive. Okay, so you normally avoid that. Okay, so this is as far as the algorithm is concerned. Okay, so just one more thing, and that is, consider a situation like this. And consider a scanline like this. Okay, at this point we have one intersection here and we have one intersection here. Okay, the edge, the edges, both these edges are just starting at this point. Okay, so we have an intersection over here. Okay, you can see the problem. If you consider this only as one intersection, then a list of intersections would be 1, 2 and 3. So all pixels between 1 and 2 will be highlighted, between 2 and 3 they will be off, and after 3 they will become on. So these pixels will become on and these pixels will become on. This is not what we want. Okay, so this, at this point we should consider it has two intersections, because there are two edges, so we should consider them as two intersections. So 1, 2, this would be 3 and this would be 4. Okay, then there will be no problem. So in such cases you should consider this as two intersections. Okay, but what happens in when you are at this endpoint? At this endpoint, if you now consider this as two intersections, you have 1, 2 and 3. There are two edges. Do you consider them as two intersections or one? If you consider them as two intersections, again you will have a problem. So here it should be considered as one intersection. Okay, so when it should be considered as one intersection and when it should be considered as two intersections?
Compare y coordinates.
I leave it up to you to decide that. Okay, you can give it some thought and then decide what will be the criteria. It's a simple criteria. You can give it some thought and get it easily. Okay, under what situations at a vertex you should consider two intersections or you should consider it as one intersection. Okay, you will have to draw a number of figures and see that whatever criteria you are suggesting, whether that is giving you correct results in all the cases. Okay, you can do that bit of thinking. That's all for today. We'll start